So, I said in the last lecture that y prime in general could depend on both x and y. And so that's going to be the focus of pretty much this whole class. So before we get into solving ODEs that are like this, we're going to first think about how to visualize their solutions. You see, in general, the general solution is going to be a function of x, but it's also going to have this arbitrary parameter c in it, right? As we discussed last time. So then, if you wanted to graph it, if you wanted to graph the general solution, you'd have to graph infinitely many functions. Ultimately, that's fine, because it's not like these functions are all going to look random. They're going to follow a certain pattern. Let me show you an example. If we have something like y prime equals 2y plus x. If you graph the general solution, you have y as a function of x. Actually, what you're going to find is there's going to be a single line that looks kind of like that, and that's going to end up being one solution. There's going to be another solution that's going to go like that, and another that goes like this, and another that goes like this, and another that goes like this. And then similarly, there are some that go like this, and this, and this, and so on. You can find a much prettier and more detailed diagram in my notes, by the way. Okay. Now, there's something to notice about these curves. They don't intersect, right? There is no point in the plane where two curves hit the same point. Additionally, if you give me any point in the plane, I can find you a solution that passes through that point. So, can this always be done? Well, what we're asking here, what we need to realize is this is a question of what's called existence and uniqueness. All right? Does there exist a solution that passes through this point? Is saying if you have the initial value problem with this differential equation and y of a equals b, is there a solution? To ask whether two curves intersect, so that doesn't happen, but hypothetically it could. To ask whether two curves intersect is to ask whether there is only one function that satisfies the initial value problem, or if there are multiple. Okay? So, a partial answer to that question is the following. Let's suppose we had an ODE like xy prime equals 1, and we made it into an initial value problem with the condition y of 0 equals 0. So these two pieces of information together are an initial value problem, as we discussed in the last lecture. So, this particular initial value problem has no solution. There is in fact no function out there such that x times its derivative is 1 and also it passes through the point 0, 0. And on the other hand, if we have y prime equals 2 times the square root of the absolute value of y, and y of 0 equals 0, this initial value problem, well, it actually has two solutions, at least. More than one, I should say. It has more than one solution. One of them is y equals 0. So just the constant function 0. The other one would be y equals x squared for x greater than or equal to 0, and negative x squared for x less than 0. Both of these are solutions to this initial value problem. So the world is not perfect. Not every initial value problem has a unique solution. Sometimes it doesn't have any. But there is a theorem out there that indicates you can count on there being a unique solution under at least one condition. This is called Picard's theorem. Let y prime equals f of x and y be an ordinary differential equation, and let AB be any point in the xy plane. If f and the partial derivative of f with respect to y are continuous in a neighborhood of AB, then the initial value problem, y prime equals f of x and y, with the condition y of a equals b, has a unique solution. On some interval. So what does this mean? Well, first of all, I don't want you to think too hard about this, because this theorem is seriously important to the theoretical underpinnings of how this class works. But as far as like exercises that use this theorem, well, there aren't many, and in my opinion, they're not very enlightening. So this theorem is important for the theory, but don't get too bogged down in the details. This is just saying that if your function of x and y, that the differential equation is defined by, if it satisfies a certain condition, then your initial value problem has one particular solution. Okay? And for the most part, that's going to be the case. For the most part, we're only going to deal with initial value problems that have unique solutions. So only one function that actually fits. So with that out of the way, let's start actually solving these. 1.3 gives us the first class of differential equations that we'll be able to solve. the separable equations. So, first of all, we have to define what that means. On ODE, y prime equals f of x and y, first order ODE, by the way, is separable if there exist functions g and h such that f of x and y is g of x times h of y. Let me rewrite that. I can do better than that. Okay. So, examples. You could have like y prime equals x squared times y. That would be separable. You could have y prime equals y over x. That too is a function of x times a function of y because it's 1 over x times y. You could have y prime equals y ln x because it's a function of x times a function of y. You could have y prime equals y squared times x cubed because it's a function of x times a function of y. You could have y equals x arctangent y because it's a function of x times a function of y, and so on. All of these are separable ODEs. They are all y prime equals function of x times function of y. So the way that you solve these is like this. You have y prime equals a function of x times a function of y. What we're going to do is a technique called separation of variables. First of all, let's write this in the Leibniz notation for derivatives. So dy dx equals g of x h of y. What we're going to do is divide both sides by h of y. If you do that, you get 1 over h of y. dy dx equals g of x. Right? Now integrate both sides with respect to x. So 1 over h of y dy dx equals integral of g of x dx. Now, a corollary of u substitution is that you can cancel these d's. So then this just becomes integral of 1 over h of y dy equals integral of g of x dx. And then as long as you can compute these integrals, you can solve the equation. Okay? So let's do an example. Y prime equals x squared times y. We're going to try to find the general solution of this thing. All right, well, first of all, let's write it in Leibniz notation. So dy dx equals x squared times y. We're going to divide both sides by y to get 1 over y dy dx equals x squared. Now, if you integrate both sides with respect to x, you'll get the integral of 1 over y dy equals the integral of x squared dx. And now, as long as we can solve these two integrals, we'll be able to solve the problem. So, antiderivative of 1 over y, well, 1 would be ln y. So ln y plus c1 on the left-hand side. And then an antiderivative of x squared would be 1/3 x cubed. So 1/3 x cubed plus c2 on the right-hand side. So at this point, we have an algebraic equation that describes our solution. If we can solve that algebraic equation for y, we'll be done. So, first of all, I'm going to subtract c1 from both sides and get ln y equals 1/3 x cubed plus c2 minus c1. Okay, c2 minus c1, since that's just an arbitrary constant minus another arbitrary constant, it is an arbitrary constant. So I'm going to give it a new name. I'm going to call it c3. All right, and then we need to solve this equation for y. Hopefully, you remember that the way to cancel a natural log is to raise e to that natural log. So we raise e to both sides. We get y equals e raised to the 1/3 x cubed plus c3. We can go a little bit further. We have addition in this exponent, right? If we have addition in the exponent, then we can write it as a product of two exponentials. So we could write this as e to the 1/3 x cubed times e to the c3. And then e raised to an arbitrary constant is another arbitrary constant. So let's call it c4. So c4 e to the 1/3 x cubed. That is our general solution, where c4 is an arbitrary constant that you can put any real number in. Okay, and this is always how these equations work. You divide both sides by the function of y, so that the y and the dy are on the same side, and then you just have these two integrals. As long as you can solve these two integrals, you'll be able to solve the problem. One thing I do want to point out, well, I guess there are two things that I want to point out about the notation that people use when they solve differential equations. So first of all, if you look closely, the reason why this is called separation of variables is because we're trying to get all the y's on the left-hand side and all the x's on the right-hand side. As of this point, that is not the case because there's still an x down here. So sometimes people will write this expression right here, or sorry, this equation right here as 1 over y dy equals x squared dx. And then they just take the integral of both sides. Now, I don't want you to think too hard about that. You look at dy dx, you're like, okay, that's the derivative of y with respect to x. I know what that is. You get dy by itself, dx by itself. What does that mean? Don't think too hard about that, okay? It's just notation for this. And it's just a sort of reminder to self that you're just taking integrals of both sides. Okay? The other thing is I got ln y plus c1 equals 1/3 x cubed plus c2, and then went from there. In practice, most people, when they do differential equations, are not this careful about what to name the constants. For them, an arbitrary constant is just an arbitrary constant. So they prefer to just give them all the name C. And then this is C as well. And so is this, and so is this, and so is that. So this isn't very careful about which constant is which, but that's okay because it's just an arbitrary constant. In other words, if you do this on your work, I will not take off points. I, for one, prefer to be more careful about it. I prefer to put the little subscripts on the constants just to differentiate them. Okay. Let's look at another example, because sometimes equations could be separable without appearing to be separable. Suppose you have y prime equals xy plus x plus y plus 1. Is that equation separable? Well, it certainly doesn't look like it, right? In order to be separable, it'd have to be a function of x times a function of y, and that doesn't appear to be. Or is it? Because if you factor this by grouping, you get x times y plus 1 plus y plus 1, and then you have x plus 1 times y plus 1, and that's y prime. So now it is separable, right? Well, to say a function is separable is to say that you can write this f of x and y as a function of x times a function of y. It doesn't necessarily mean that what those functions are will be obvious. So in this case over here, there exist functions of x and functions of y that you can write this as a product of, even though that doesn't appear to be really clear at the beginning. So it is separable. And so we can use separation of variables on it. dy dx equals x plus 1 times y plus 1. Divide both sides by the function of y. We get 1 over y plus 1 dy equals x plus 1 dx. And then these are just integrals. Right, so an antiderivative of 1 over y plus 1 would be natural log of y plus 1. And an antiderivative of x plus 1 would be 1/2 x squared plus x. And there better be a plus c, right? If you're wondering why there's not a plus c on both sides, it's because if you did have a plus c on both sides, then you could just move it over to one side and then rename it c. That is what we did over here, after all. So we could just put it on one side, and that's fine. Anyway, we're going to have to raise e to both sides of this in order to cancel the natural log. So we get y plus 1 equals e to the 1/2 x squared plus x plus c. Subtract 1 from both sides, you get y equals e to the 1/2 x squared plus x plus c minus 1. And then again, we have addition in the exponent, so we can write this as e to the 1/2 x squared plus x times e to the c minus 1. E to the c we could rename as, I don't know, c0. So then this becomes c0 e to the 1/2 x squared plus x minus 1. And that becomes our general solution. Okay. Let's try another one. Another separable ODE. Suppose you have dy dx equals y squared plus 1 divided by x squared plus 1. This is separable because it's a function of x, specifically 1 over x squared plus 1, times a function of y, specifically y squared plus 1. So we can do separation of variables on it. The way to do this is we have to divide both sides by y squared plus 1. So we'll get 1 over y squared plus 1 dy equals 1 over x squared plus 1 dx. Caution. At no time should you ever have 1 over dx or 1 over dy. In any case, those things just don't make sense. In any case, these are just two integrals set equal to each other. The antiderivative of 1 over y squared plus 1 with respect to y would be arctangent y. And then an antiderivative of 1 over x squared plus 1 with respect to x would be arctangent x. And there better be a plus c in there somewhere, right? And so now you just take the tangent of both sides. You get the general solution. Y is the tangent of the arctangent of x plus c. And there is our general solution. Now, When you are doing differential equations, you sometimes run into algebraic equations that can be rather difficult to solve, sometimes impossible. When that happens, what you're going to have to do is present that algebraic equation and say, this is, whatever solves this algebraic equation is the solution. And I'm done. That's called an implicit solution of the ODE. Okay? So let's see how that works. Find an implicit solution of y prime equals x over y. So, again, separable. So dy dx equals x over y. Multiply both sides by y, and you'll get y dy equals x dx. And then these are just integrals. An antiderivative of y would be 1/2 y squared. And an antiderivative of x would be 1/2 x squared. And there better be a plus c in there somewhere. So, y squared equals x squared plus c. If you're wondering what happened to the 2, it got absorbed into the constant. At this point, this is your answer. It's an algebraic equation that the solution will satisfy. And that's what I'm asking for if I'm asking for an implicit solution. Sometimes that's just the best you can do. All right, let's try another example. Y prime equals sine x over cosine y. So again, write this in Leibniz notation. Dy dx equals sine x over cosine y. Then do some algebra to get all the x's on one side and all the y's on the other side. So cosine y dy equals sine x dx. And these are just integrals, right? So an antiderivative of cosine y would be sine y. An antiderivative of the sine of x would be the negative cosine of x. And that's about the best you can do. So let's leave that as an implicit solution. There are some of you who might be thinking, can't you just say y is equal to arcsine of c minus cosine x? And the answer is maybe. The trouble is that the arcsine function only returns values that are between negative pi over 2 and pi over 2. So if your y isn't bounded between those two values, then it's not necessarily valid to write this. So, no. In general, when I give you a problem and I'm only expecting an implicit solution, I'm going to tell you. And when I expect an explicit solution, one where you have y by itself equals something, I'll tell you in the directions. Okay? So there's just one more thing to mention about separable equations. It's this thing. This is called the exponential differential equation. If k is positive, this is called an exponent. Sorry, let me be clear. K is a constant. So k is a constant. If k is positive, this is called an exponential growth. And if k is negative, then this is called an exponential decay. In Calculus 1, you might have seen this before. Now, though, you actually have the theory about how to solve it. This is separable. You can write this as 1 over y dy equals k dx. And then these are just integrals. An antiderivative of 1 over y would be ln y. An antiderivative of k, well, since k is a constant, that would just be kx. And there should be a constant, arbitrary constant c in there. So when you raise e to both sides, you get y equals e to the kx plus c, which is e to the kx times e to the c. And then if we rename e to the c as a, this is y equals a e to the kx. And so we get an exponential function, just like you would in Calculus 1. Okay? In any case, that's about all for today, so I'll see you in the next one.